Okay, this is the second hour of Physics 1B for September 8th, and just wanted to start off by going back to this problem and just asking, does anyone have any questions or comments about this before we go forward? Do you all understand why the answer is B or C? Just to kind of refresh, the idea was that by putting the chest beneath the raft, you give it an additional force from the water, which will reduce the load that's acting on the raft by some small amount to allow the raft to run as high as possible. Make sense? Okay, good. Okay, so we're going to do another problem, and then I have another kind of conceptual problem that's a little trickier than the one we just did. So let's just make this large enough that you can see it. Is this readable for everyone? Okay, so this is a Archimedes principle problem about Archimedes. Okay, so Archimedes supposedly was asked to determine whether a crown made for the king consisted of pure gold. This is a kind of, I don't know if this is true or not. That's why it says according to legend. Supposedly, the story goes like this, that the king was given a gift. Is this the king of Athens? Maybe. I don't really know. I was given a gift by another ruler of some nearby town or city state or something like this, and the king suspected that the gift was not pure gold, and so Archimedes was was a very renowned scientist. I guess let's put it that way. As if I don't even know if the word scientist would have existed back then. Was very renowned, maybe engineer. I don't know, someone that dealt with problems like this. And so the king asked him to figure out whether it was pure gold or not. And immediately Archimedes didn't have an answer. And so he went home and he was thinking about it. And he thought about it for a few days. And then one day he was lying in the bathtub, floating in the bathtub, and starting to realize, like, oh, when something floats in water, it doesn't weigh the same amount. And so he supposedly screamed, "Eureka!" That's why this thing is titled Eureka. And Eureka is just, an expression people use to mean like, oh, it's like a light bulb effect. That's what Eureka means, right? And in Greek, it means to discover. So by saying Eureka means, oh, I figured it out, basically, is what I've discovered the answer. And so supposedly then, because he was so excited that he figured it out, he didn't put his clothes on and he just ran down the street naked to go tell the king what he'd figured out, forgetting that he, had been taking a bath. So whether that's true or not, I don't know, but it's kind of a good story, and it's stuck with us through the years, so it shows up in these kind of problems about Archimedes. So according to legend, he solved the problem by weighing the crown first in air and then in water, because that's the idea, right? It's going to weigh less in water, right? And the difference between those two weights should tell you if it's gold or not, basically, right? And you can always just use a test sample, right? You can use something that you know is gold and then see what the difference between the weights is, right? And then he can do the same thing with a crown, and if the difference isn't the same, then there's a problem, right? Okay, so here's all the information that we're given. It says, suppose the scale read 7.84 newtons when the crown was in air. So right here, the scale is reading 7.84 newtons. Now, they wouldn't have measured things in newtons back then, but, for our problem, that's what we're measuring it in. They would have measured it in, I don't know, stones or something like this. I don't really remember what their unit of measure was. And then 6.84 newtons when it was in water. So this is the scale reading when it's in water. 6.84 newtons. And the question is, what should Archimedes have told the king? Is it gold or is it something else? That's what we have to figure out here. So what we're going to do to figure out if it's gold or not is we're going to use the knowledge that we have that we've kind of set up so far, and we're basically just going to calculate what is the density of the object. And in this case, it's a crown, right? So we'll use the subscript crown. So we want to find what is the density of the crown. And then when we know what the answer is, we can go compare that density to the density of gold, which we can obviously look up, right? So that's our goal here, is find the density of the crown based on this information here. I want you all to solve this yourselves, but I also want to get you set up so that you are on the right track. So in order to do that, we'll just kind of slowly go through this. What would you suggest we do first? What do you all think the right first step should be here? Oh, I just saw your question, Matthew. I'll come back to that. Sorry. Yeah, but what would you do? How would you start it? Draw the net force? That's a great idea. So start drawing forces on both crowns, right? Okay, great ideas. Let's do it. So on this crown here, what we would have is just a weight, obviously, but then there's one other force, which would be the force that the scale is pulling up with, right? So we'll call that force, I don't know, I like calling that kind of force tension force. So this tension force then, I would say, is obviously going to be equal to the weight. So really, the tension force is kind of what's read out by the scale, right? All right, so for this one, let's go ahead and analyze it. This is kind of a silly analysis, but net force equals 0, which means the tension minus the weight is going to equal 0, which means the tension is equal to the weight, which tells us that the weight of the object is 7.84 newtons. Okay, that's not too surprising, right? That doesn't tell us much. So basically, the first reading, all it really tells us is what the weight of the object is, but that's going to be useful. Now, on the second object here, we're going to have the same weight acting on the object. That doesn't change. We're going to have a tension that's acting upwards. Now, this tension is less than the weight now. So we'll draw it a little bit shorter. And we've also got a buoyant force, which is acting up on the object now. So we'll just kind of like draw a line to the side and then indicate it as a buoyant force pointing up like this. So now we've got a buoyant force, a tension force going up, and a weight going down. And again, the system is in equilibrium. There's no acceleration, right? So we should also be able to say in this case that the net force acting on the crown is equal to 0, which would mean that if I take the buoyant force plus the tension force, because they're both going upwards, and I subtract the weight, that should be equal to 0. Now, let's call these things something different, because these are different. Let's call this one T1, and let's call this one T2. And then acknowledge that this is T2. And then throw a little subscript here and a subscript here and here, just so that it's clear. Forgot that those tensions were different. I should not use the same symbol. I apologize for that confusion. Okay, so everyone said write out the forces acting on the crown, and then I went one step further. The obvious next thing to do once you've written the forces is to apply the equilibrium condition to get a relationship between those. Okay, does this setup make sense? And does anyone have any questions? Now our goal was to find the density of the crown, right? So, what do we do? How about you all try it yourselves? And I will put up here, so is this a full submersion or a partial submersion problem? Is our crown fully submerged? It's full submerged. Okay, so that means we can go back and we can use our full submersion equation, right? Let's go back. I think that's the first equation we had, right? Full submersion. We just used this one, right? So we'll come back down and we'll rewrite it. So for full submersion, what we have is that the buoyancy force should be equal to, you take density of the fluid, you multiply by the volume of your object. In this case, our object is the crown, right? So we'll just put volume of crown. And you multiply by g, right? So I want you all to try to solve this yourselves. So I'll give you like 4 minutes, I think. So it's 11:16, so about 11:20. So, and I will also, while you're doing that, I'll pull up the density of gold. Okay, so try to solve for the density of the crown given this information. Take your time. Maybe one more minute. Okay, that was about 5 minutes. So, oh, let me just address something real quick here. Matthew, you said something about this previous problem. You said, would the chest floating or sinking make a difference in scenario C? No. As long as it's tied to the thing, it shouldn't make a difference. All right. What do people say here? Okay, so yeah. So what's the next step? What do we do next? What do we do next? I was trying to get rid of the bar on the top there, but I guess I can't. You know, you don't have to type. You can. When I ask, you can open your mic. Find the weight of the crown. Okay. You wrote in the buoyancy formula and then the weight? Okay. All right, let's do those things. So buoyancy, we can see up here, is going to be equal to the density of our fluid, which is water, times the volume of the crown, and then times G, plus T2 is something we already know, minus. Now, when you say weight is density, yep, there you go. Density of object times the volume of the object times something else. That would give you just mass, right? So the weight of any object should be equal to its density times its volume, because that's mass, right? Rho V is mass, times G. So we can put those in here. Rho crown, volume crown, times G. This is all equal to 0, and there is the thing we need to solve for, right? Right there. But we have two unknowns now, right? We know what T2 is. We obviously know what G is. We know what the density of the fluid is. But we have another unknown, right? What's the other unknown that we have? Density of crown's an unknown. What's the other unknown in this equation? The volume of the crown, right? We also don't know what that is. So we're going to need at least one more equation, right? The crown's volume. We do not know what that is. So we don't know this, and we don't know this. Those are our unknowns. Okay. So we need another equation, right? What's that other equation going to be? There's multiple ways to do this, too. I don't know which way you chose to do it. Did anyone get an answer, by the way? You don't need to put the answer in the chat. Just curious. You can just say yes if you got an answer or not. You got one. Okay, cool. So how do we deal with this, the fact that there's these two unknowns? What's the other equation that you all used to get an answer then? What did you do? You subbed in mass over density for volume. Okay. So you're going to use the fact that we know the relationship between volume and density is that volume is equal to density divided by mass? Is that right? Wait. Density is mass over volume, so volume would be mass over density, it'd be the opposite. But I'm just wondering, we don't know the mass of the crown either, right? We don't know the mass of the crown either, right? So we'll try this, but I'm worried about the fact that we don't know the mass of the crown either. Or maybe we do. Maybe. Well, we'll just see how you did it, because there's definitely a way to do it. Ah, we know the weight of the crown from T1. That's exactly right, Christian. And that's what we're going to use. We're going to use this equation. Right here, right? Yeah, exactly. Okay. So how we go about doing that, I suppose, doesn't really matter. We know that this weight, though, is also equal to the density of the crown times... Okay. Here, this is the part that I think is maybe the easiest way to do this, instead of going through all these different steps. Notice that the weight right here, we subbed in density of crown, volume of crown times g right here, right? But isn't that the same thing as 7.84 newtons? i.e. it's equal to just what the tension was here. So what we could plug in here... Whoops. Now this is no different than what you all did. I'm not trying to say this is better. It just happens to be the case. This is also equal to T1. And now, how many unknowns are in this equation? There's just one, right? Just the volume of the crown. So let's just solve for that from this equation, and then we can find the density from the other equation. Let's do that. That works, right? So we're solving for volume of crown, right? So we'll go rho f v crown. There's definitely a way to do this all in one step, but I think it might be even easier to do it in two steps, or at least clearer. Okay, so the only difference here is we basically just said, oh, the weight is the same thing as this tension from the first part. So we'll just plug that in here. And then we're solving for volume of crown. So volume of crown is going to be equal to T1 minus T2 divided by the density of water times G. So we know all this stuff. We won't see it if I keep writing there, so we'll go down a little bit. So volume of crown is T1 minus T2. So that's 7.84 newtons minus 6.84 newtons divide density of fluid. It's water, so 1,000 kg over meter cubed. It looks like something's getting cut off there. I promise you that's not. 9.8 meters per second squared. And that will give us the volume. The volume should be in meters cubed. Look at the units and make sure that's the case. Looks like the numerator is 1 divided by 1,000 divided by 9.8. So this is going to be something 1.02 times 10 to the negative 4, I think. Oh yes, it loves doing that when I write force. It should be meters cubed. I think it is always, always, always worth your while to check out your units. So let's just briefly, we'll come back to the problem. Let's just look at the units right here and make sure they actually give us meter cubed, because if they don't, we made a mistake, right? So what are the units? We've got newtons. A newton is a kg meter over second squared. We're dividing by kg over meter cubed. And then we have a meter divided by second squared. You can see pretty clearly that this whole unit up at the top cancels out with that whole unit right there, and you do get meters cubed. No matter how long you've been doing physics, you should do this pretty much with every single problem. I've been doing physics problems since I was 16 or something like that. And when I first started, I didn't do this stuff. And it wasn't until I was halfway through grad school that I started realizing how powerful this is. And it's mostly because when you solve really long problems that involve manipulation of algebra, and this is not a hard, long problem, right? We only did a few steps of algebra. That doesn't mean I didn't make a mistake, though. It's very easy to make a mistake. In addition, you might put units in the wrong form. Like if you put something in centimeters or something like that, it's going to cause you a problem. But the cool thing is that once you get down to this final relationship right here, by checking the units on the right-hand side of the equation and making sure they actually give you volume, you almost virtually guarantee that you did the problem right. You know what I mean? Because if you did the problem wrong, and your g was in the numerator or something like that, the units would show you that it was wrong, okay? So it's a good way to check whether you did the problem right, and when you're doing an exam, it's one of the most valuable things you can do. is after you've finished the exam, go back and look at all your final answers, and then look at the units and make sure they make sense. You don't even need to look at the part where you put the units in, because you could have made a mistake there, right? Just look at this step and say, what are the units of T? Well, it's force, so it's newtons. This is kilogram per meter, oops, sorry. This is kilogram per meter cubed, and this is meter per second squared. So this is how I would always check my work when I did tests. And I would always do this because it's just the best way to figure out if you made a mistake or not. So anyway, getting back to the problem, we found the volume right here, right? We just found the volume. And we now want to use that to find the density. So now we can just go back to what equation? This equation? We can use this equation to find the mass of the object, and then we can use the volume and the mass to find the density, right? So this equation, we know that 7.84 newtons is equal to the weight of the object, so that's equal to the mass of the object times gravity. So we can solve for mass from this equation. So we get that the mass is going to be 7.84 newtons divided by 9.8 meter per second squared. Calculate that, and then we'll put them together and find density. Now, we could have done this entire problem in one large equation, but I think, personally, this is a little bit easier to understand. Maybe it's not, though. So our final answer will be that the density of the crown will be equal to that mass divided by the volume of the crown. And that is going to be 0.8 kg divided by 1.02 times 10 to the minus 4 meters cubed. Put this in a different color. What are the units of newtons? It's this right here, Troy. A newton is a kilogram times a meter per second squared, and you can remember that because F equal to ma, so mass times acceleration. Mass, and then acceleration. Okay. Alrighty, density of crown is this. We end up getting that the density of the crown is I'm just going to write this in scientific notation as 7.8 times 10 to the 3 kg per meter cubed. Now I got 7840, but it's going to depend on how many decimals you keep and stuff like that on this denominator. So this is the answer. And is that the same thing as the density of gold? Nope, because the density of gold is 19,300. This is closer to the density of maybe like aluminum or lead or iron or something like that. I don't really know. I think it's less than the density of iron, but we could go look it up. In fact, what we could do is we could figure out what the likely metal that would be is. So we could go look at density of metals and be like, okay, well, now that we know the density, what is it likely that that is? Are these sorted by number? No, but here's something called Babbitt. I've never heard of Babbitt before. Brass, bronze. It looks like bronze, right? Didn't we get 7.8? Yeah. So this is the density of bronze, which bronze obviously kind of looks like gold, right? Iron / steel in the book you're saying is common to that. Let me see here. Where's iron on here? GHI. Oh, it is close to iron. Yeah, so it's iron or steel. Steel also, yeah. So it looks like it's a combination, or could be a combination of many different metals that they get for this answer right here. Those metals would be very common, whereas gold, of course, is much more rare and a lot denser. Control F would help me to find those, but luckily in this particular case, Pat, it is in alphabetical order, so it's not that hard to find them. Okay, so yeah, there we go. That's the Archimedes crown problem. Does anyone have any questions? This is a nice problem because within it is a lot of calculations that are going to kind of have to be second nature to you, meaning that you got to be comfortable with the idea that weight of an object is related to not only mass times gravity, but it's also related to its density and its volume. You know, remembering that kind of stuff will be very important to you. All right, any questions? We'll do one more conceptual question here. So this is one you can actually try at home if you want to, okay? So take a glass of water. In fact, you could do it in the next couple hours during this class. You could set this up right now and you can check to see if it's correct at the end. Okay, so if you happen to have a desire to do a little bit of a experiment at home, then try this out right now. So all you're going to need is ice and water. So hopefully you've got some ice, maybe in a freezer. I hope you have access to water. And you probably want a glass that is... I mean, it doesn't have to be a glass. It could be plastic, I guess. But glass would be nice just for seeing what you want to see for this right here. So here's what we're going to do. We're going to take a glass and we're going to fill it with water, right? And then we're going to put ice into the water. Okay, so you're going to have ice cubes. And what do ice cubes do in water? Do they sink? No, they float, right? Because ice is slightly less dense than water, which is a unique property of water, isn't it? Aren't most solids, the solid form of any type of a liquid, is usually denser than the liquid? Does that make sense? Water is unique in the sense that ice happens to be less dense than the fluid. So I'm pretty sure this would only work with water. Maybe there's some other fluids where this is true of. Anyway, point is, if you put ice into water, right, it tends to float. Does it float like on top of the water, like a boat? Not really. Some portion of the ice is beneath the water. In fact, we kind of did a problem earlier where we figured out that the majority of the ice is actually going to be beneath the water, maybe up to 75% of it, right? So we've got ice, and it's sitting here on top of the water. Now, the question of this problem is going to be about the water level, okay? The way we do this demo at the school is we fill up a test tube, not a test tube, but like a beaker, like a tall graduated cylinder kind of thing. We fill it up with water, and we put ice into it, and we ask the following question. What happens to the water level after all the ice melts? A is that it rises. B is that it goes down, or lowers, I guess. And C is that it stays the same. And again, you can try this yourself. What we do in the lab is we fill up a graduated cylinder with ice water, and then we wrap a rubber band around the top so to mark the water level. So you could do the same thing, or you could take like a marker and you could mark on the glass, right? Mark where draw a line where the water is, right? And then it takes a while for all the ice to melt, right? Of course, you could set it outside, it would melt really fast. And yeah, so that's the question. I want you all to think about this for a minute or two. Think about what your answer is, and then I'll do the same thing as I did before. We'll have everybody put the answer in the chat at the same time. That way no one can influence each other. And we can just stick with what your intuition is. So, take a minute or two. Think about it. Actually, before you start thinking about it, does anyone have any questions about the setup? Does the setup of the problem make sense? Fully submerged. Well, that's a great question. Is the ice going to be fully submerged, or is it going to be partially submerged? What do you think? Doesn't ice float on water? So that a portion of the ice is going to be sitting out of the water? It does, right? You can check it yourself. Go put ice into a cup. You can go do it right now. Step away from the computer. It's partial submersion. Yeah. It's partial submersion. Okay, does the question make sense? What happens to the water level after all the ice melts? Here, while you all are thinking about that, I'm gonna go see if I have a glass that I can fill with water just to prove what I'm saying. Be right back. I don't know how well you can see this, but like the ice just ever so slightly is above the water. Does that show up on the camera very well? Again, if it doesn't, you can try this at your house. But the ice, like especially like over here on the edge, you can see that the ice sticks above the water basically. I've tried to draw a line on here. I don't know if I did a very good job where the water is. And I'm just going to leave that. We'll see what happens over the class. All right, so let's do the same thing we did before. I hope that was enough time to think about this. Is it enough time? Do you need more time? Okay, so just type, but don't push enter. Type your answer in the chat, and I'll tell everyone to type it at this. I'll push enter at the same time. With all those climate change messages, I hope not. You'll have to tell me more about what you mean. Okay, so go ahead and get ready to push enter in 3, 2, 1. Push enter now. Whew, it all comes in so fast. Okay. Let's look at these answers. Okay, so B, C, A, C, 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 B, A, C. All kinds of different answers. A lot of C's, though. It seems like C is the majority. Just glancing through these. Looks like C is the majority. Okay, and Keanu said C due to the displaced liquid caused by the ice cubes, but you're kind of down for A. So to you, A feels correct, right? It feels correct, but you're saying that your science is telling you C. Kind of sounds like. Christian says, because the water is already displaced by the cubes. Ah, so what do you mean by that? The water is already displaced by the cubes. That's an interesting statement. What do you mean? So I think you're saying something along the lines of the cubes have displaced some amount of water, right? They've displaced this amount of water that's beneath the surface. And you've got some portion above the surface, right? There's more people typing. I'll let you all keep typing. Yeah, feel free to type your reasoning into the chat now. Now that you've all answered, feel free to type your reason. I'm not going to tell you what the right answer is. Not right now, at least. Well, I'll tell you as soon as we've discussed it more. Okay, so the ice that's slightly above the water will slightly increase the water level after it melts. Yeah, so you're saying basically that when this ice up here melts, it's that melted ice is going to raise the water level. That's a very nice intuition. Not saying it's right or not. I'm just saying that's a good reasoning. Matthew says, since only when it melts does the volume of once the ice cubes occupy the water fully. Since only when it melts does the volume of the I guess water once the ice cubes occupy the water. Because the ice cubes are not fully submerged, the water level will rise up only by part of the submersion, and after fully melt, the water level will fully rise. Okay? Ice expands when it freezes from water. If you fill a water bottle of water with water completely and then freeze it, it expands and sometimes break the bottle. Exactly, that's right. Therefore, my reasoning would be that the water level will lower because it's the reverse of that. That's very interesting. I like that. Okay, so you put C because you thought we were comparing the level of the water once the ice was put, and when the ice in the water, it expands to its volume, so once it melts, the level is the same. Okay, that's very logical. Like Christian said, the volume of the water is already displaced, so any melted water volume rise has already been accounted for. Interesting. So that's an argument for C, Astrolover, is that right? The volume of the water is, yeah, okay. That's very reasonable. Maybe the water level lowers because when the ice melts, the mass stays the same, but the liquid form will have a lower volume. Okay. You all are making a lot of very reasonable points. I think the most natural answer, like just the first thing that springs to mind when I see this problem, and this problem was presented to me, I didn't know what the answer was. It was given to me at a job interview, and it's also something we use at Onizuka Science Day to challenge students. We have these students come and we do these science demonstrations. This is one of them. This is one of the questions we ask. I think this is the natural thing you'd want to say. You'd think, okay, well, certainly when that excess ice melts off, the water's going to raise. And I think someone said almost exactly like that. This was my first inclination when I first saw this problem, was this feels like the right answer. But as many people have said already, a lot of you said all the right things to get to this point. The thing is that there's a reason why there's a little bit of the ice that's actually slightly above here, right? There's a reason. And it's because in this form, right? In this form, the ice has less density than water. So the ice is occupying more volume than it would when it gets turned into water form, right? Would you all agree with that? That the ice is currently, in its current form, the ice occupies more volume than it will when it turns into water. Would everyone agree with that statement? Once the ice turns into water, it's going to have less volume, right? How much less volume will it have once it turns into water? How much less volume will it have when it turns into water? Can anyone answer that question? How much less? Is there any way you can describe it based on the picture? No idea. There is a way to describe it based on the picture. It may not be so obvious. How much less volume will the ice have? The bit at the top. That's exactly right, Christian. That is exactly right. This is exactly how much less volume that the ice will occupy. That part. The part that's above the surface, right? That's how much less volume the ice is going to occupy when it's become liquid. So just think about this, like, yeah, it's floating on top of the water, but as soon as the ice melts, its volume will be just that much less, meaning that piece at the top will be gone once it melts, and the liquid water level will stay the same. That's the right answer. This is the answer. It stays the same. That's a very tricky problem because it tests our intuition about density, about what buoyancy is, and about different forms of liquids and liquid and solid states of matter. So it hits upon a lot of different ideas that are all kind of important in science. And we can check. We can test with my water here, but feel free to try this yourself. It is super easy to try this at home. It is super easy to try this at home, right? All right. It is 11:47. We have one more problem. Oh, there's a couple more, actually. I want to do this one, and I want to talk about these. Maybe the most reasonable thing to do is to talk about the barometer first, because we have just a little bit of time before I want to take a break. And then, yeah. How late does this class go again? It's still like 12, or it's like 1 o'clock, right? 12:50 or something like that, I think. I think it's till 12:50. Did anyone have any questions? Sorry, I gave the answer and then we didn't really talk about it that much. We talked about it, and then I listened to your explanations, and I tried to use those to inform how I explain this. But does that explanation make sense to everybody? Why it stays the same? Mostly because when melted, the ice will occupy less volume, and the amount will be the amount that was above the surface. Yeah. Your brain is processing. That's okay. Think about it for a minute, yeah. Well, we'll come back to this right before the break, and you can think about it. Let's talk about ways to measure pressure. So, we have talked about what pressure is in this class, but we haven't talked about how exactly you measure it. Because in science, of course, you can't just talk about a thing as a concept alone. You need to have some way of quantifying it so that if I measure a pressure and you measure a pressure, we can agree on what that pressure is. And if you use an instrument to measure pressure and I use an instrument to measure pressure and they're different from one another and you get different answers, we need to be able to have a consistent conversion factor that proves that both devices can actually produce a number that is meaningful, right? So drawn here is a mercury barometer. I often find that when you see a picture like this, it is very confusing because, can I push this off to the side? I can't. I don't care about the first one. We're just looking at the barometer for now, okay? So the first thing we're going to look at is a barometer. Now I find that when you see a picture like this, it can be a lot to take in. So I'm going to try to build it from scratch, and then we'll go back, because the picture is better than what I'm going to draw, but I think it helps to like see things drawn from scratch. So what is a barometer? Okay, simplest way to make a barometer is the following. You take a some type of a dish of some sort, okay? And then we fill this dish with mercury. What's a good color for mercury? I guess this color is fine. So we're going to fill this dish in here with mercury. So mercury, the symbol for that is Hg. In case you don't know, for some reason, mercury is a liquid at room temperature, and it's also a metal. It is one of, I believe, only 2 things on the periodic table that are liquids, right? There's mercury and there's one other liquid. What's the other liquid at STP? Right? There's one more liquid on the periodic table, right? Maybe a lot of you haven't taken much chemistry. I don't know. It's bromine? Anyway. So, liquid mercury, it's a liquid at standard temperature and pressure, and it's very, very dense. The density of mercury, it's probably on this right here as well, since it's technically a metal. Yep, right there. Density of mercury is 13,530. Let's write that down because we're going to need it. 13530. You had a choice between chemistry and this. A choice was made. You made the right choice. I always think you should study physics before you study any of the other sciences. I know that that's not very reasonable, but anyway. So this is the density of mercury up here. So we'll just write that this is the density of mercury. You can see that it is significantly denser than both the density of air, which will be something that's relevant here. Density of air is, I believe it's like 1.2 kg per meter cubed. Okay, so it is significantly denser than air. Significantly denser than air. Okay, next thing you do is with this mercury right here, we're going to take a thin, empty tube, and we're going to place it upside down inside of this. Maybe we'll use a different color. So we're going to take a thin tube, and we're going to place it upside down inside of this, okay? And what is going to happen is that when this tube is placed into here, and we submerge it underneath the mercury here, so we submerge it underneath the mercury, what happens is that air pressure acts from the outside on both sides, all around on the mercury here. And that air pressure exerts a downward force on the mercury. And because there's a downward force on the mercury is going to travel up the tube. Remarkably, it will travel up the tube. You need to have a very tall tube for this. At least like, let's see here. What color was I using for that? We're using this one. So the mercury will end up kind of filling up the tube up to a certain point, up until the point that the pressure inside of here is going to be 0. I've been using capital P for pressure. Pressure is equal to 0. So there's like basically a vacuum created near the top right here. And the height of that column of mercury is going to be proportional to the air pressure outside. So when the air pressure goes up, the column will go up. When the air pressure goes down, the column will go down. Okay? And that's pretty much how you do it. And then what you do is you just go in here and you just put a bunch of markings on here, right? And you basically just say that the height of the mercury column is proportional to the air pressure. Now we know what air pressure is, right? Let's say, for example, let's let the pressure of the air be equal to 1 atmosphere, okay? And let's ask the question, how high is the mercury going to rise? So this is the height. If the pressure is 1 atmosphere, how high up H is the, right up here, H. How high is the pressure, or is the mercury going to rise? So this is kind of like a balancing act that's happening, where the air pressure pushes down, but if you have this column that's entirely filled with mercury right here, the whole thing is filled with mercury from top to bottom, that mercury is going to exert a downward force due to its weight. And we know that if you have a height of mercury that has that's exerting this pressure, we have our variation with pressure with depth equation, right? Which tells us that the pressure exerted by this column of mercury should be equal to whatever the pressure at the top up here is. Let's go ahead and call this P0. No, I don't want to do that because we're using P0 for atmospheric pressure. Let's call it P top. Let's just call it P top. The pressure at the top is 0. Oops. Top. Okay. So pressure at the top plus you take the density of your fluid, which in this case is the density of mercury, you multiply by gravity, and then you multiply by the height of the column. This is our variation of pressure with depth equation. And that will tell us what the pressure is right here at the surface of the mercury, where we know that the external pressure is 1 atmosphere. So all we have to do is to figure out what height h makes it so that the pressure here is the same as the pressure of the air. Because if the pressure created by this column of mercury is the same as the air pressure on the outside, that's the balancing act, right? The air pressure ends up being equal to the pressure from the column of mercury, then they're balanced, and that means that the column of mercury's height will tell you something about the air pressure, right? So pressure at the top is 0. All we need to do is to make it so that the pressure from the air is equal to this quantity. And if we solve that for h, let's go over here, we get that h is going to be equal to the air pressure divided by the density of mercury multiplied by g, right? So h is going to be equal to, we have to put air pressure into pascals, so I'll put 1.013? It's 1,013,000, yeah. So it's 1.013 times 10 to the 5 pascals, and then divide by the density of mercury, which we have up here, 13530 kg per meter cubed, multiplied by gravity, so 9.8. Doesn't look like this is getting clipped off. And that's going to give us an answer of the height. We'll scroll down just a little bit here. And if you calculate that out, I think you're going to get a height of about 7 or 0.76. Yeah, 0.764 is what I get out of this. 0.764 meters, or 764 mm. This is usually measured in millimeters. So if you set something up like this, and the height of the column is 0.764 meters, that's kind of a long distance, right? It's a little under 3 feet. So the height of this object right here, your tube that you place in here, would have to be at least 3 feet tall. So that's like half the height of a person, right? The version of this that we have at the lab, which I'll show you when we go to the lab, it's quite big. It's really big. Anyway, that's how we first started measuring pressure with the mercury barometer. I can't remember who invented this, if it was like Pascal or Torricelli. I think it was Torricelli. I don't know. I have to go look it up again. I can't remember off the top of my head. I knew at one point. That's something you all could tell me. Maybe you could look up who first invented the barometer. Maybe you all know. Maybe someone knows. But yeah. Does that make sense? How you could use this to measure pressure? And if it had a reading, so this is how you end up measuring the pressure here. And I think someone mentioned this early on. An alternative way to measure pressure instead of using atmospheres or pascals is to use millimeters of mercury, okay? So 1 atmosphere of pressure then is approximately equal to, we'll use approximately because I think books usually use 760. So it's approximately equal to 760 millimeters of mercury. This is the unit. It's a very nice unit. It involves a periodic symbol and millimeters. So millimeters of mercury. This is one way you can measure pressure. And when you look up conversions, you'll see that you can see pressure measured in bars, millibars, pascals, atmospheres, millimeters of mercury. Pressure has maybe the most different types of units associated with it. I don't know if the most, but it has a lot of different options. Okay. Anyway, okay, so that's one example of an object we can use to measure pressure. Does anyone have any questions? I don't think my explanation was particularly great, so I'd encourage you, if you want to learn more about barometers, maybe go read more on your own. I tried to set that up, and it was Torricelli. Okay, thank you. Pretty clever device as a way of measuring pressure. Alrighty, so we have to take a break as we're at the time to do so. So we'll take a 10-minute break. We'll start again at 12:10. And I'm just going to show you what we're doing next, and I'll let you think about it yourselves. Because this is directly related to a homework problem that I get more questions about than any other homework problem in this class. So that is why we are going to make sure we cover it. And I believe it shows up in a lab manual problem too. So this is what we're doing when we come back. Feel free to read it if you want to. It's from your textbook. Let me go ahead and stop the recording.